Hello everyone, my name is Rafael Eduardo González Marin, and today we are going to be doing a project for the Laboratory of Computational Physics. And in this day, we are going to solve a project for the heat equation with realistic boundary and forcing conditions for a daily thermal simulation over the Yucatán Peninsula. First of all, we are going to have our objectives aligned. We want to simulate the evolution of temperature in Yucatan over a daily cycle using the heat equation. We have to consider the solar insolation with hourly variation. What does this mean? Well, we are going to simulate the sunrise and the sunset of the sun, making it like do a like to travel from east to west to simulate the heat in over the Yucatan Peninsula. We have to consider the thermal difference between land and sea. This is because in the land is way hotter than in the sea because of the winds surrounding it. We have to consider our variable dissipation and coastal profile, meaning that in this case we are going to have a dissipation of heat regarding time due to the wind of the coasts and the sea, and of course in the inner continent we have different variation of wind because of the three places have different wind velocities. We are going to consider heat transport via advection and diffusion, meaning we are going to consider the heat regarding the sun and the diffusion of the heat regarding the wind, the velocity of the wind of the different places that we mentioned before. Uh, the following thing that we are going to consider is the problem review and why simulate temperature. Why doing this project about a like weather simulation? Well, of course, it is important, but temperatures model help understand local meteorological phenomena. As we told before, we can simulate the different temperature of the different places only using a heat equation and to consider different things as wind, humidity, and even height of the place that we are considering. And of course, Yucatan coastline presents well-defined coastal microclimates, meaning that if cities are in the coast, they are cooler than cities that are in the inner continent. This is obvious because we have a bigger wind velocity in the coasts, and we have that the sea makes the place a little bit cooler and have different climates than the inner continent. And the simulation can be applied in climate, urban, and energy studies. Of course, cities are way are way as I was saying, cities are way hotter than the rural places or the coast cities, meaning that in urban places like Mexico City or Merida are hotter than places like Cancun or Progreso. So it is something to have into account. We have the theoretical background of our equation. We modulate this equation using the heat equation, but also we have a advection and source terms that where K is the thermal diffusivity, U is the advection velocity, the zonal wind, Q is the solar forcing term, like the heat that the sun produces, C per T minus T base represent dissipative cooling towards the base temperature. So this model structure is widely used in environmental and engineering applications, including underground heat transport, as said in Minet and Dufresne 2023, Urban Heat Island Modeling as said Rodriguez Lopez and Hernandez Cruz 2024, and Numerical Solutions of Advanced Heat Equations as said in Vejot and Bess 2022. Moreover, recent advances apply this framework even to geometry adaptive models using deep learning, as explained in Huang and Cheng 2020. Meaning this is very useful and resourceful equation and model to consider for real life applications. At the right side of the slide, we can see a lots of constant use in the Python simulation that we made. In this case, we consider a base temperature of 26 degrees, the maximum land temperature of 42 degrees, the maximum sea temperature of 30 degrees, and dissipation is stronger at night and inland. The coastal profile has a smooth the coastal profile is smoothed with Gaussian filter. These considerations are because we can have the same temperature regarding in the sea than in the inland because of the wind velocities, and we consider a maximum land temperature of 42 degrees because we use a average of data of on summer of the Yucatán Peninsula, and in average it is about 42 degrees at its peak hour in the day, that is at 2 p.m. and the base temperature is 26 degrees because at night that's the lowest temperature that is reached. So we are now uh, we have now the numerical method used for this project to solve these heat equations. We solve it using a explicit finite difference method on a 2D grid. We have three key aspects. The first one is a spatial derivative. We use central difference for second order accurate. We have a time integration using forward Euler method for first order accurate. We have a smoothing Gaussian filter applied to simulate terrain diffusion as applied in Vejot and Vest 2022. We have our boundary conditions for north and south borders. We put a Dirichlet condition of temperature for 26 degree. It is a constant degree, and we have a Newman condition for the derivative of space, or the derivative of temperature regarding space is zero on east and west borders. This ensures numerical stability and avoids artificial edge effects, as mentioned in Minet and Dufresne 2023, Rodriguez Lopez and Hernandez Cruz 2024. Now we have our results, and at the left side we have the simulated map for temperature of our Yucatan Peninsula. And what do we observe? Well, we have that a land sea temperature gradient, meaning that in the coasts are cooler than in the inner land. We have a thermal peak around 2 p.m., as we said before, because it's where the sun uh, is at its highest position and temperature. We have a rapid decrease of temperature after sunset because we don't have a heat source anymore, and the wind forces dissipate the heat. We have a coastal dissipation that prevents to overheating near the shore. As I told you before, the shore is cooler than in the inner land, and the sea is way cooler than both of them because of the wind velocity uh, involved in each of the three considerations of land. We have that the peak temperature is around 40 degrees, as represented in yellow, and we have that the lowest or the coolest temperature is about 25 degrees, as presented before. It is used these numbers only as a frame of references because this can vary it regarding your simulation and regarding the time of the year that you are having this simulation. We have the numerical errors that the first one is the truncation error caused by approximating derivative. The second order in space have a truncation error of a step squared, meaning that for each spatial step that we are using, we have that w- with a smaller step, we have an increment of truncation error of square of itself. And for the time, we have a first order and a truncation error of around delta t, meaning that when the step is smaller for time, we have the same truncation error. It is linear. And these are expected properties of the explicit time difference scheme as set in Bijot and Vest 2022. We have the stability error, the CFL condition, CFL meaning current Felix Lewis. Explicit methods require small time step to maintain numerical stability, as we all know. And in our simulation, uses dt equals 0.1 h, meaning that is the size of this of our step, and this satisfies the CFL condition for the chosen thermal diffusivity kappa, preventing divergence or instability as set in Lee, Shang, and Wang 2023. Smoothing error, Gaussian filter. We applied a Gaussian filter to suppress high frequency numerical noise. This is only used to prevent a like bigger different temperatures in one place to another without being like normal. It is something. It is considered something to be more smooth, as its name said. This introduces a non-physical diffusion, but helps stabilize the simulation and maintain spatial coherence, as said in Juan and Cheng 2020. We have that this analytic solution didn't have a exact result, but the simulation showed consistent realistic thermal behavior across different time steps and great resolutions, in line with validated models of urban and environmental heat transfer, as mentioned in Rodriguez Lopez and Hernandez Cruz 2024, and in Minet and Dufresne 2023. We now have our conclusions. And in conclusion, the heat equation, when combined with numerical methods, proved to be a powerful and versatile tool for simulating a wide range of heat transfer phenomena. Its application extends from meteorology and climate modeling, as we said before in our project, to material science, engineering, and even space research. This demonstrates how mathematical modeling not only help us understand complex physical processes, but also play a crucial role in developing new technologies and solving real-world problems. Uh, in short words, we can say that this is a powerful, resourceful, and very useful tool, the heat equation with dissipation terms for modeling real heat transfer problems in our real life, or even for as astrophysicists to see or to model galaxies in the outer space. It is a very, very useful and versatile tool. So it is a crucial equation that we need to understand better to use it more frequently in our daily life, and to to be given the credit it's deserved. Well, we have our references for this project, and I'm glad to have presented this to you. Thank you very much. See you later.